Thank you so much.
Great. Yeah. Okay. This is great. Yeah. I guess I can start. Can you see my screen,
Yeah,
Ali? And
yeah,
oh, okay, great. All right. Yeah. Thanks for inviting me. Thanks for having me here. So, it's great to be back at MIT, although virtually. So I'm Jiajun Wu. I'm a new assistant professor at computer science, Stanford, and I started July last year, so like half a year ago. And before that, I spent a year at Google, and before that, I got a PhD at MIT. So I still feel it's not too long ago, and remember all those IEP activities and everything. So that's great. Yeah, my research is in general C understanding. So humans can see the world and understand the world and understand by understanding the scene. We mean many things. We understand objects. We recognize object categories, but we also understand objects 3D geometry, their material and texture, physical properties, how what's going to happen in the future. So all of these things are part of human see understanding abilities. And my research is about how we may replicate those abilities on machines. Drawing inspiration from human cognition, but really to build machines that can not only classify cats as versus dogs, but have a holistic, see understanding ability. Ali, is that is that responding to your question? Like
yes,
giving some
yes,
background? Yeah.
certainly. That's great. If your students have questions, please ask Jiajun. He's very
Yeah,
friendly.
because I cannot really see the chat. So, either
Yeah,
Ali, you can let me know if there's a chat
of
question
course
in the
I
chat,
will
or
keep you.
or students can just unmute and ask directly. Yeah.
Certainly.
Okay. So yeah, today I'm going to talk about, I try to talk about part of my research that is most relevant to this IAP seminar because it's about, deep learning for arts and aesthetics and stuff. So here we try to think about how we may integrate AI or deep learning, but with domain knowledge, especially, those domain knowledge from computer graphics. The world is made of objects. Objects have surfaces. There are like higher level procedures or regularities among objects. How we may use these domain knowledge from computer graphics and integrate them with machine learning. So instead of doing pure end-to-end machine learning, is what such kind of a hybrid model allow you to do things that you cannot do before, such including in downstream applications such as image editing or this kind of image generation. So these kind of things could be closely relevant to how you can use deep learning for creativity. Okay, so before I start, I mean, I should emphasize that this is really joint work with many people, and especially the students. Xiaoming, Zhou Tong, they're still currently PhD student at MIT, and Jiajun, Yikai as well. Yikai is a visiting student at MIT. They really did most of the work, and they should take all the credits for the things I presented here. Also, this is joint work with my advisors, Bill Freeman, Josh Tenenbaum, my Google collaborators, Noah Snavely, and Jing Yan, who is now assistant professor at CMU, was a postdoc at MIT, and longtime collaborator of mine. And I think he's also speaking, or he has already spoken at this seminar, or maybe in the future. But I saw his name on the website. So
Yeah, he gave us a
you
talk
also
about yeah, he gave us a talk about efficient GANs. Was pretty technical.
okay, great, yeah. So you have already heard from Jing. Yeah, that's great. Yeah. Okay, so scene understanding, right? I want to integrating learning and graphics for 3D scene understanding. So what do we mean by scene understanding? If I show you a picture like this and ask you, do you understand the scene? You actually understand in many different dimensions. You can easily recognize there are some cars and you can count them and answer the question, how many cars are there in the scene? You understand objects have attributes. So you can answer, some objects are closer, some objects are far away, and objects have colors. So what's the color of the closest car? Right? It's black. You also understand objects have 3D geometry, so you can imagine, how would the car look like from the front if you see it in the other direction. And the scene is not only static; it's dynamic, right? It looks like the person who took the picture is also in a car, so you can imagine what's going to happen. The person is probably going to move forward, and the other cars are going to move forward as well. It's not only about objects, but also there are scene descriptions. Right? It looks like a cloudy day, but what if it's rainy? Then how would the picture look like? Your ability to understand scenes is not only restricted to these familiar objects, objects like cars, trees that you see many times in your life, but also it's can be applied to even novel objects. Here's a pile of toys or random objects, and some of them you have seen before, and many of them you may have not seen before. But your ability to understand scenes also applies to novel objects or novel scenes, including those that you have even maybe never seen before. So can we do that? Let machines have these abilities as well. So to do that, we can start with a kind of a simple problem, relatively simple problem, compared with the thing we saw before. That is, if it's possible for us to first recover the 3D geometry of the object from a single image. Here we assume that the image only captures one object, the object centered, and all we care about is to get the full 3D shape of that object from that single image. Okay, so in this problem, if you think about the other direction, right? If I'm already having the 3D shape, how can I produce that 2D image? Then this is a classic problem in computer graphics, because you can, if you know object shape, texture, lighting, and material viewpoint, then graphics, right? The part of the graphics is rendering. It can actually produce that beautiful 2D pictures for you. Is like for computer vision, we often care about the other direction, the reverse problem. Now, can we inverse graphics to actually reconstruct the 3D shape from that 2D image? And this is why computer vision, like 2 decades ago, a lot of people say, oh, vision has inverse graphics. But these days, people may see computer vision slightly differently, because they're like, okay, now we have deep learning. So instead of doing inverse graphics, we can just throw in a giant, complicated neural network that takes a 2D image and magically output a 3D shape, especially in cases where you have a lot of training data for. If you can collect a lot of paired supervised training data of 2D images and 3D shapes, maybe a deep network can just do all the work. But as I said before, our theme here is we wonder if there's any, I would say, inspiration or priors or domain knowledge from computer graphics that we can borrow and we can integrate with deep learning systems, so that maybe the deep learning systems can perform better, or can be more efficient, or can be more generalizable. So to answer this question, let's first take a deeper look of how the image formation process, the forward process, works. If I have a 3D shape, it's a 3D, so you can see it from the back. If you have a 3D shape and you want to understand the forward process, right, image formation process, how does it really work? Here, this is a simplified visualization. So you have the 3D shape, it's in the 3D space, and there's a light source. The light source sends a rays to the objects, hits the object, hit the surface of the object, get reflected to the camera. And in front of the camera, there's an image plane. So you're seeing from the image plane a picture of the object. So think about what you're really seeing here. Are you seeing the full 3D geometry of the object? Not really, right? All you're seeing is the visible surface of the object. Right, this is why on the image you're seeing the chair has 3 legs. You're not seeing the 4th leg because it's not visible. It's occluded. Of course, you understand, right, that the chairs must have 4 legs because you have prior knowledge of what chairs often look like. You have prior knowledge that chairs are often symmetric. Chairs must be stable. So therefore, even if the 4th leg is not visible, you understand the chair still has 4 legs. Right? But essentially, what you're seeing from the picture, if you just think about a single image, then you're only seeing the visible surface, including 3 legs. Okay, then we wonder if we want to do vision as inverse graphics, take things kind of graphical representations into learning systems. Maybe we can design the learning system to do the inversion also in 2 steps to solve the shape estimation process problem in 2 steps. The first step is to estimate the visible surface. Now here we choose to estimate the depth map. You can see the depth map, whether every point is closer or far away from the camera as a reparameterization of the visible surface, right? Essentially, the depth map is representing the visible surface in some different representation. And the second step is to take the depth map and to complete a shape going from depth map to full 3D shape. So why we choose depth map as an intermediate representation, instead of other possible intermediate representations? This is because depth map, as we said, is a reparameterization of the visible surface. And visible surface is essentially all the things you can see about object shape from the input image, right? Although the visible surface or the depth map doesn't capture the 4th leg, there's nothing from the image I can learn or infer that the chair has 4th leg. Right. The second step, shape completion step, has to really rely on my prior knowledge. Therefore, in machine learning, the term is have to be learned from a large data set of other similar shapes. right? I need to see a lot of shapes that are also symmetric and stable, so I can transfer knowledge here to complete the shape. And the first step is really about, okay, can I try to extract as much information about object surface, about object geometry as possible from the color image, right? So a different way to say that is, okay, once you have the depth map, you conditional depth map, then input image and output 3D shape becomes like conditionally independent. This is why you choose that as the intermediate representative. It's not like arbitrary. It turned out, if you design a system like this, you have two smaller deep networks, and you can train the network, two networks on ShapeNet is a large data set of 3D CAD models. You can randomly sample shapes from them from ShapeNet, put them in random poses in front of random backgrounds. So you can train on synthetic data of images, depths, and shapes, and you can test it on real images. Here is results on the real images from Pascal 3D Plus dataset, which is a kind of pretty challenging dataset. You can see that some of the chairs are not that normal, not that common. And this is what we will get if you train an end-to-end deep network without modeling depths. And this is what we will get with modeling depths, using depths as an important intermediate representation. It turns out it's such a small change, right? A very simple, straightforward change, but greatly improve the results. Right now, you can see the output is looks much more close to the ground truth, and also captures some of the details in the shapes. This is because depth map really forced the system to focus on object surfaces, which are what really matter to human perception if you care about 3D reconstruction. Here are a few more results. Again, by having depth map as an intermediate representation, the output is more accurate, contains more details. So this is joint work with Yifan Wang, who is now a PhD student at University of Washington. Okay, at the beginning, we said our ability to understand scenes also generalized to novel objects, including objects we've never seen before. How would this model work if we try to test or generalize to unseen object classes? If we take the model trained on chairs, planes, and cars, these are like the three largest object categories from ShapeNet, and then we test it on the table. It's also, it's still furniture, right? Relatively close to a chair. You send it to the network, and this is what you get. Well, it doesn't look like a table. It looks much more like an airplane. Why is that? Because the system has never seen a table, and now it's given a table. It's like, okay, what is that? Okay, the top of the table looks like some of the airplanes I've seen before. It's kind of flat and thin. So I'll just retrieve a nearest neighbor airplane. This is not only a problem to our model, but also a common problem of many single image 3D reconstruction approaches using different 3D representations, including point clouds, voxels, meshes, and collection of surfaces, and all these different representations. So for people who are interested, there is a paper called What Do Single View 3D Reconstruction Networks Learn from CVPR 19, which analyzed this problem in detail. So you're welcome to look into that paper if you really want to understand why this is happening. Okay, so now our question will be, is that possible for us to solve this problem, right? To build a model that generalizes to novel object classes. Again, we would like to think about if there's anything that we can learn or borrow from the graphics and from this top-down rendering process. If we look at the second network, the shape completion network, right now it takes a depth map and output a 3D shape. It's true that it's essentially just learning how to complete a 3D shape. But depth map, although it's a reparameterization of the visible surface, it's still a 2D image, right? It's still in 2D. And the output shape itself is in 3D. So implicitly, the shape completion network has to learn to back project depths into 3D, right? It has to learn to back project a 2D representation back into a 3D representation. But on the other hand, projecting depth or back projecting depth into 3D is a deterministic and fully differential process because it's implemented perspective projection. It's implemented in every graphics engine, right? Every graphic engine has that. It's deterministic and fully differentiable. In that case, if this is something we already know, deterministic and fully differentiable, why do you have to let the shape completion network to be over-parameterized and relearning that deterministic mapping? That seems like a waste of capacity, right? So our solution here is, what if we just build that into the network as a differentiable layer? So now the system works as I estimate the depth, and then I back project it into a partial surface or the visible surface in 3D. As you can see here, it's now in 3D. Still, it only has 3 legs because the fourth leg is occluded. It's not visible, but it's now in 3D. This projection layer is implemented as a neural network layer, deterministic with no learnable parameters, but also fully differentiable. Okay, so you can still do end-to-end training. And then the second shape completion network now takes this partial shape and completes, gets you the full shape. Now, if we take the model trained on chair, planes, and cars, same as before, we tested on this table. This is what you had before, and this is what you have right now by modeling depth and projection. So with two simple changes, one is an important intermediate representation depth map. The other is an important differentiable layer back projection. The system now works so much better. But if you look at the top of the object, the surface, then you realize there's still some issue. The surface doesn't seem to be that smooth. We have a prior that the surface of tabletop of these man-made objects are often very smooth. This is because partial surface in 3D is very sparse, right? Most of spaces in 3D is like empty spaces. So it's hard for the completion network, which is purely in 3D, to capture surface features because a lot of the expressiveness are wasted to represent empty surface. This is not only a problem for the tables, but if you test it on the chair, even the one from the training object categories, and this is the output. From the input viewpoint, it looks like, okay, this is good. But if I rotate it, right, this is what you see. It's not like the shape completion network is doing nothing. It's doing something. It knows that things must be connected. It must be roughly symmetric, but still, it doesn't have enough power to represent a smooth surface. So our solution here to further improve the pipeline is to use spherical maps as a surrogate representation for surfaces in 3D. So we can have an object and a partial surface. What is a spherical map? You put it in 3D into a unit sphere, and then you sample rays from the surface of the sphere. And for every ray, you record the distance it traveled until the moment it hits the object. Okay, so if you parameterize the ray in azimuths and elevation, like a UV mapping, then this is what you get as a spherical map. So what's important about spherical map is every pixel on the spherical map, you can see every pixel here represents or corresponds to a point on the surface. Right? Because every pixel here is recording the distance that then a ray traveled until the moment it hits the surface. Right? So no representation power is wasted. The surface representation, the spherical representation is completely focused on surface. And here we can, instead of back projecting depth into a 3D partial shape, we can back projecting depth into a spherical map or a partial spherical map. So then the system becomes, at first estimated depth, and then it projects into a partial spherical map. And then you want to do the completion instead of in 3D. Now you do it in a spherical map space, right? You want to complete the partial spherical map and make it into a full spherical map. So the problem becomes now an imaging painting problem. And because spherical map only records the first time every ray hits the object, right? So it cannot deal with things like self-occlusion, as you can see here. So you can back project the spherical map after completion into 3D. It's almost complete, but there's some minor issue with self-occlusion. So finally, you have a small refinement network to complete the shape. This becomes the full pipeline. And then now if you test it on still the same table, trained on chairs, planes, and cars, this is what we get with direct prediction. This is what you have by modeling depths and back projection, but without using spherical maps. And this is what you get with spherical maps. Especially if you compare the top of the surface, right now the output is just much smoother. Okay, so this is the main idea behind our work called generalizable reconstruction. Build a system that can reconstruct 3D shapes from a single image, but in a generalizable way, even applicable to object categories that you've never seen before during training. Back in Europe's 2018, joint work with Xiaomi and Jiajun. They're both PhD students at MIT, and they really did all the work here. Some more results about our system genre, generalizing to unseen object classes. Here's now we tested, still trained on chairs, planes, and cars, and we test them on bookshelves and sofas. Here are some input images and the baselines. The baselines are doing okay, actually, not terrible. You can see that they're trying hard to approximate input shapes. And here's our reconstruction, which is much better and have more details. Again, you can compare with the ground truth to see that there's still, of course, imperfections and places to improve, but it's getting close. If we look at what is really happening, how does the network able to complete the backup the sofa, which is not visible in the input, then we can visualize it and see, the back of a sofa, which is not visible, is becoming missing values in the partial or single view spherical maps. After it goes through the completion or now the spherical map impinging network, this is what we get as a full multi-view, or I would say omni-view spherical map. Impinging network has learned to imping the spherical map to be smooth so that it can actually complete and reconstruct the 3D shape. Here are some more results on beds, tables, and benches. Again, training our chairs, planes, and cars. Here are the results from baseline. So you can see that it's trying very hard to approximate the input, using chairs or using airplanes, but it's not that accurate. And here's our reconstruction. It'll even get some of the details like the holes in the bed, as well as the legs of the bench. Also, you can compare with the ground truth as well. We also even tried to generalize to non-rigid object classes. So what if we tested it on humans and horses? The system has only seen chairs, planes, and cars, but now we tested on humans and horses, these non-rigid object classes, and these are our reconstructions, and these are the ground truths. Of course, you can see a lot of bumpiness and still imperfections here, but it's quite remarkable that the system, without seeing any deformable objects, are able to roughly get a sense that objects or shapes must be complete and smooth, and are able to reconstruct humans and horses in a relatively reasonable way from just single view. Okay, so here we have talked about how we may use intermediate representation, surfaces, and back projection, as knowledge from computer graphics, but integrate them with the learning system so that you can build a shape reconstruction or vision system that perform better, but also much more generalizable. Now let's look at the other direction, how this intermediate representations, which people often call like 2.5D surfaces, like surface like depth map is an intermediate representation, how that may help you to also make the rendering better. The rendering we already said in computer graphics, you take the shape, you take the texture and lighting and viewpoint and everything, you can produce that picture. But how could learning be helpful? In computer graphics, you have to require that you already have the shape, have the texture, have the lighting, and have everything. But what if I want to synthesize new object shapes and new object textures? So now let's look at this from the other direction. We have been going from left to right. Now let's look at how it works from right to left. So together with Chen Kai, back then was an undergrad at MIT and later become an MEng. So we first extended generative adversarial networks to 3D. I think people here are familiar with generative adversarial networks, so I'm not going to repeat that. But we extend that to 3D so that you can synthesize 3D shapes. But later when Jiajun came to MIT, then we thought, okay, maybe we can actually do better because Jiajun is really an expert in 2D GANs and cyclogans and everything. So we thought, once we have the 3D shape, maybe we can do a forward projection. So now we do still the same thing, differential projection and surfaces, but now we work in the other direction. We take the 3D shape, we do a forward projection. We can compute the silhouette and the depth of that 3D shape under a particular viewpoint. And then we can apply a 2D cyclogan to apply textures on these depth map and silhouettes so that you can synthesize not only 3D shapes, but the corresponding 2D pictures of these 3D shapes, right, with textures. This is nice. And also there's a benefit of this kind of hybrid system because now you have a separate representation for textures and viewpoints and shapes. So you're able to do control over these independent factors, right? So you can say, I want to see the object from different viewpoints, but maintain the shape and texture. I want to synthesize different shapes, but under the same texture and viewpoint. Or I want to have the same shape and viewpoint, but I want to change its texture. You can do that for chairs. You can do that for cars. You can also do interpolation. I have two objects with the same texture and pose, but I want to interpolate their shape. I can interpolate their texture. Or I can interpolate both. I can have two objects in the same viewpoint, but with different shape and textures. I can interpolate both textures and shapes. I can also do transfer. Now here I synthesize 3D shapes using a 3D GAN, but now I've seen other pictures of cars. I think, oh, these cars look really nice. So how would the texture of these cars look like if I apply them to the shapes that I synthesized? How would my shapes look like if I have the textures from those images? So here we represent 3D shapes still as voxels, and later there's some other follow-up actually from a different group. And also now there are many more, but I think this is like the representative one, where they extend our shape representation, 3D shape representation from voxels to an implicit function, so like latent vector. So now your 3D representation becomes like 4D because it's no longer like 1 or 0 occupancy. It's like a latent vector. You can still do 3D transformation and projection, but now you can actually synthesize shapes, synthesize images with an even higher quality. Okay, so we talked about how we may use the intermediate representation, especially this 2.5D surface, knowledge from computer graphics, representation of surfaces, and projection, 2D to 3D back projection, 3D to 3D forward projection, to help us to build better vision systems that reconstructs better, generalize better, and also better graphic systems that can synthesize new objects and new textures. Now, what if we put everything together, and then we can try to extend them to scenes? So here is the scene of there are a few cars on the road. It's kind of like foggy. And I can first run my inversion systems so that I can get, interpretable representations of objects, their geometry, their pose, and their textures. And here, because I'm extending that to scenes, right, there are things like trees or skies that are not really like object-like. So I also represent these segments as a latent vector. So in addition to objects, I have these kind of latent representations for the background segments. Okay. So now I may wonder, how would the scene look like if I move the car to the right? Because right now they're mostly at center. So I can actually edit the representation. I can move the car to the right, and then I can send this edited representation back into the augmented or the hybrid graphics engine that we just talked about. So you can synthesize and reconstruct the image, but now with everything else staying the same, but the position of the car changed, the car moved to the right. So this is joint work with Shunyu Yao and Harry Xu. Harry is a PhD student at MIT, and Shunyu is now a PhD student at Princeton. So we can do image editing on virtual kitty. We can see, okay, there's a car that's really far away. So how would the image look like if I move the car to be closer? And now you can see the car much more clearly. Of course, the network has to come up with how the car look like, right? Based on the limited observation. You can imagine how the car look like if we see it from a different viewpoint. How would it look like if it's facing to the right, if we're looking at it from the front? How would the scene look like if I change the texture of the car? Or if the scene is rainy? Or if I have objects, multiple cars on the road, and how would the scene look like if I remove one car? But the notion here is very important. It's like we know that objects, the scene is made of objects. Objects have surfaces. Objects have 3D geometry. Therefore, if I remove the car in the front, then I should still see a complete car in the back. Right? I shouldn't see kind of a blurry but smooth in painting results. But instead, I should be able to see a complete car in the back, because to understand cars have 3D geometry and there's occlusion going on. I can keep removing the car until there's only like one car left. These are results on the virtual kitty dataset, which is synthetic, but we also have results on real images from the cityscape dataset. You have original images, and you can edit it. You can say, okay, what if I move the car closer? What if the car is facing into a different direction? Or what if this is the picture I showed at the beginning? What if there's a car that's really far away? And how would the scene look like if I move the car to the center, move it closer, or move it to the right? On real images, you can see that the textures are much more complicated. There are a lot more details. And therefore, our method is not working that well, because you can see if you look very closely, it seems like some of the background is not really actually being maintained. But in general, it gives you a reasonable image editing results. Okay, so we've talked about how we may use 2.5D surface and back projection and forward projection as intermediate representations for completion, reconstruction, for rendering, but also now for putting things together for scene understanding and for scene image editing. So this is all about using knowledge from computer graphics, objects, the notion that objects have surfaces, there is projection. But maybe you want to go a little bit higher, to a higher level, if you look at this example, right? Again, we're going back to this table, and we have a table, image of a table. We have results from direct prediction, genre without spherical maps, and full genre. Now it looks like, okay, the top of the table is smooth. Still something is wrong. If you really look carefully at the top of the table, then you find that, okay, we have such a strong prior humans that the top of the table should be like round, because it's man-made objects, then all the tabletops should be round. But here, it's not really round. It's like a weird triangular shape. Right, but this problem is really hard to solve from just this input image, because if you look at the reconstruction from the input viewpoint, then it looks really close to the input image, right? There's almost no information that you can obtain from the input image to actually infer that the top of the table is round. So here you want to go a little bit higher level, right? You want to go from a shape reconstruction to shape abstraction, because we understand that shapes, especially man-made objects, they often have abstract and program-like representations, right? Looking at this table, you have a strong understanding that the four legs must be identical and they're regular. They must be also on a 2x2 grid in terms of layouts. Okay. So how can we encode those kind of strong prior information into our shape reconstruction process? We made a first attempt. We actually designed something we call the shape domain-specific language, which is try to explain in the form of a domain-specific language what man-made objects or at least furniture should look like, and we design the language themselves. And now instead of reconstructing shapes into this like raw format such as voxels, if you do reconstruction into shape programs, then the top is now round and matches our intuition much better. Due to time constraint, I wouldn't have time to talk about this in detail, but for people who are interested, happy to chat offline if people want to understand more about how the system works, like how procedures can be applied to shapes for better reconstruction, better modeling. Joint work with Yonglong Tian, who is also a PhD student at MIT. Okay, so we're going from objects and surfaces and now to programs, and see how this may help us to understand and model scenes, especially objects, from just like 2D images. But such kind of rich structure or procedurals, it didn't only exist in shapes such as chairs or tables. There are also a lot of rich structure in 3D scenes. So what are these structures? There could be like planes and surfaces, right? And if I'm in a corridor, then okay, I know there are multiple planes and they have a certain configuration. And scenes can be symmetric, and also it could be repetition, right? I know that the lights in a corridor must be repeating themselves, and the windows are on the building is repeating themselves as well. So can we actually leverage this kind of priors, such as repetition and symmetry, for like content creation, for example? So here's a demo that we made using the GUI from Adobe Photoshop. So we're hoping that Photoshop can do this, but Photoshop currently cannot really do that. So we actually made the demo using the Photoshop GUI, but with the technology or the algorithm we developed ourselves. So what we can do here is, now I have a building. I can use interactive segmentation to segment the building. This is actually from Photoshop. But now here comes our own algorithm that we try to, based on the vanishing point, is smartly detect the repeating objects. Here is the windows, and use that to guide our editing or design of the building. Like we make it much taller, then how would the building look like, right? In that case, now we have such a strong prior, again, as humans, that the buildings, or at least the windows, should be really repeating themselves and following that, but also respecting the 3D perspective projection. So how can we do that? Right, let me tell you about the algorithm. In computer graphics, there has been a lot of research on trying to model these kind of structure or procedures. For example, there are out systems. It's quite remarkable that with very simple rules, you're able to explain very complex hierarchical structures. There are like probabilistic context-free grammars, all those methods for representing and modeling 3D, especially things like buildings. But these things purely focusing on 3D, right? They don't really connect to 2D images. So it's not from like 2D observations. Everything works in the 3D space. So to connect to raw 2D images, we're inspired by this very first work, actually, also from MIT, from Josh Tenenbaum and Amando's group, where they try to do program synthesis for visual data. So if you observe an image like this, 2D line drawings, what they did is they first infer using learning and stochastic search to find some low-level primitives like lines and triangles. And then going from those lines and triangles, they do program synthesis, learning program synthesis to infer a latent program for that explain those primitives like lines and triangles, their regular, their layout, their configuration. And then they can easily manipulate the program for extrapolation. Right? Now you can see that's another hand drawings with more complex patterns. So inspired by that, we also tried that on 3D primitives. we're like, okay, now if I have a 3D, I'm living in a simplified 3D world where every object is either a sphere or a cylinder or a square, then, maybe I can also try to detect a group of objects. These are like primitives. And then for those primitives, I can try to synthesize the shapes or programs for those 3D shapes. And then you can actually use that, to guide your image synthesis. I was like, okay, how would the scene look like if there's not a column of Lego blocks? So these kind of works are interesting, but both this 2D line drawing and this 3D primitive work, they have very strong limitation. That is, how could I generalize to natural images? If I have shown you natural images of milk and cereals, clearly there is still some program like structure or procedures there. But how to represent a cereal, right? Those entry-level primitives are easy to model in line drawings or simplified world, but how could lines and rectangles or cubes or spheres generalize to real world? Because real world objects could be arbitrarily complex. So our idea here is to resort to internal learning. So internal learning is about learning everything from a single image from image statistics. It was originally proposed by Mihaly and Irani's group in 2011. And the key observation here is, within a single image, patches are very likely to repeat themselves, right? The repetition can happen at same scale, like those red boxes. It can also happen at different scales, like those green boxes. Because of what? Because of perspective projection. Objects that are closer could be larger, objects that are far away could be smaller, but they could be essentially the same objects. So the repetition can occur across scales. With deep learning, people have also tried to explore this idea in deep learning. The one work in 2017 is they're like, okay, if I take an image and if I send them into like a preaching neural network, like Alex said, and then I can get all those activations. And then I can, for all those activations, compute if I translate them, right, by a certain amount, then how would the cross correlations be? How likely would the activations to be repeating themselves? And then based on the translation, I can actually compute what are the translation X and Y that maximize those kind of correlations. So why is this important? Because those X, Y's are most likely to be the intervals between repeating objects, right? So if I have multiple objects that are essentially the same, and if I translate image or translate activation maps by the amount, then it's most likely that in the activation maps, they're going to be strongly correlated. Why do we do that in the activation space instead of in the raw pixel space? Because in raw pixels, the raw pixel can be influenced by a number of factors like lightings, like occlusion, like background texture variations, like even the capturing noises during the image capturing process, right? But neural networks, especially Alex style, those kind of stuff, if it's trained to classify the image, they're designed, they're supposed to be invariant. The activations are supposed to be invariant to these kind of noises, perturbations. And so this is why they use neural network activations to find repeating objects in a single image. We adopted a similar procedure. Of course, we made some changes, but essentially the main idea is like this. We adopted this procedure, we applied it onto our image, and it will allow us to find repeating objects in the image. So this is now like the primitives, like the lines and rectangles in 2D line drawings, or like the spheres and cylinders in the 3D scenes. But now we're able to use neural network learned features to identify repeating objects or primitives, and then we can synthesize a program on top of the centroids of these repeated objects. Everything else is like essentially the same, except that now we're explaining the low-level primitives with neural network learned features. Okay. So this can help us to solve a number of problems. For example, if now I show you an image with a missing patch, I want you to complete the patch. Of course, you can just put in some textures, but because they're repeating crosses, right? So I was like, okay, I have such a strong prior that I need to put a cross there. So you can actually use your synthesized program to identify what are the patches that should look similar, I should use or I should borrow to complete the image. And I can identify all those repeating patches, similar patches using the knowledge from my synthesized programs, send it to another image completion network, and to actually complete the image. Right? So now you can see there's another cross being completed and put into the image. And if you look very carefully, it's not identical to any of the other crosses in the image. So we're not just simply retrieve a patch and put them together, but we're smartly blending all other elements that should be similar to the missing region and produce another cross and make the image look realistic. The program can also allow you, to do extrapolation as we see before, but now on a real image, you can add another line of crosses. Or the programs can tell you how regular the scene is, right? How much every centroid is deviating from the supposed center specified by the program. So you can actually do regularity editing. You can magnify those kind of irregularities. You can do that on the serial image as well. I can say there's one piece that is missing, and I can, I should be able to paint it with another piece of serial. I can do extrapolation, adding another column of serial. I can do regularity editing to make the scene more irregular. Here's some more results on real images. I want to do ink painting. Again, there was some, regular structure. So I can use my program guided image manipulators to actually complete the shapes, also respecting regular structure there. And you can compare them with ground truth, and it's actually pretty close. And you can also compare with the baselines. The baselines, some of them are actually doing reasonably well, like patch match, but still there are like some ghosting effects and stuff, which are not ideal, where our method can actually do better. The graded comb, actually, it's a learned neural network-based method, which actually does a quite a reasonable job, but it's reasonable locally. If you put it back into the global, the entire image structure, then you find that it's not really respecting the repeating structure in the image. Okay, so here we have shown how program can guide us to do image manipulation on a single 2D image. But if we really want to do that for 3D scene understanding, going back to the corridor example I showed before, then the 3D scenes has multiple planes, right? Is it possible for us to generalize our method that only was applied to a single plane, now to multiple planes? It turned out to be possible. The program will be much more complex. Now, first, you have to set a camera and a viewpoint in 3D. And then you have to identify each place. What are the planes that really partition the image? How should I really partition the image into multiple planes? What are their orientations and surface normals of each plane? And then I can do program synthesis on each plane. Okay, so the partition part is actually really challenging. Before we said, for 2D or for line joints, the primitives, the visual primitives are like lines and rectangles. For 3D, it can be cylinders and spheres. For natural images, we can use neural network activations. But for 3D plane partition, what would be the low-level visual cues? Here we say the low-level visual cues can be vanishing points, the 3D vanishing points, as well as the wireframes. So it's kind of conceptually, there's kind of analogy here, right? We use lines and shapes as the low-level bottom-up visual cues for line joints. We use repeated objects for single-plane images. And here we use vanishing point and wireframes for multi-plane images. But these kind of things, when you try to solve a more complex problem, those low-level feature extraction problems also becomes much harder. So if you look at, for example, the wireframe, it could be like very noisy. So how would I be able to, use these kind of going from this noisy observation of wireframes to actually find the correct partition of the plane? Now, if I just rely on these wireframes, there could be multiple possible candidate plane partition, right? Some of them are correct. One of them is candidate 2 is ideal, but 1 or 3 are incorrect. But you can't really tell that from this wireframe features. Our solution is we can actually address that by our top-down knowledge of programs. So you can actually first do plane rectification. You can say, I have multiple candidates. I don't know which one is correct. Okay, I did assume, for each one, I always try to rectify the planes to unwrap the planes into, from 3D into a 2D image for each plane. And then I try to do program synthesis on top of that. And the observation here is only if you can do the plane partition correctly, you will be able to synthesize a good program of it. If your partition is like terrible, it's totally off, then things from multiple planes will get folded into a single plane, and the results after unwrapping will be just terrible. And there's no way you can find a good program that very well explain the plane information. And only if you can partition the plane correctly, you will be able to easily synthesize a nice program that explains the repeated structure, like these repeating lights in a single plane. So plane partition and program synthesis can really help each other in those cases. And by finding the one that the program can really explain the partition plane, you also simultaneously find the best plane partition. Okay, you solve two problems at the same time and letting the bottom-up visual cues and top-down program structure to talk to each other and to find the best joint optimization results. With this, you're now able to do view synthesis. You can imagine how the scene will look like if I walk forward, compare with baselines, which can actually do really well for general image synthesis. But here, if you ask them to do things that are really challenging, like keep going forward, extreme image synthesis, then they become very blurry because they don't have those kind of higher notion of, okay, objects repeating themselves. These are like program-like representations. You can also imagine how the scene will look like if I look to the top left. And, I should expect another light to come in, right? This is like really important. And those baselines cannot really do that. Or how the scene would look like if I walk backward. Or how would it look like if I turn around, right? So this is now becomes like the infinite corridor at MIT. I think one of the original inspiration for me to do this is like, okay, there's an infinite corridor at MIT. Can we replicate the infinite corridor in computer vision? Of course, in practice, no corridor can be infinite. But if this is the single image is all your observation, then I guess the most plausible imagination of how the corridor will look like if you turn around is there should be like an infinite corridor where the lights are repeating themselves. You can also do image extrapolation, right? You can model these planes not only from inside, like a corridor, you can model it from outside, like a building, so that you can do extrapolation. And this goes back to the demo I showed that before, where you can use that to guide your image extrapolation. You compare them with the baseline. Some baseline actually give you some reasonable synthesis results, but they don't really respect the input image. And ours works the best. Okay, so finally, to summarize, we talked about optics, the notion of surfaces and projections, as well as later procedures on objects and also on scene structures. How this domain knowledge from computer graphics can be better integrated with computer vision or with machine learning for us to reconstruct shapes, synthesize shapes and textures, and to use those higher level programs or procedures to guide our understanding of scenes for scene synthesis for content creation. And the key innovations here is we know that neural networks are just remarkable at extracting complex patterns from visual data, no matter how complex the pattern is, right? GANs or ResNet very good at classification for capturing low-level details for style transfer. On the other hand, the domain knowledge from computer graphics or in general, like objects and surfaces and procedures seems to be very good at generalization, right? Of course, we should be very careful here because if you want to use too much domain knowledge, it can actually hurt your generalization because some of them may be specific to certain scenarios. But the knowledge we took here, objects, surfaces, and 2D, 2D projection and procedures are really universal, right? So the takeaway here is we're only exploring the causal structure behind visual data. Why are we seeing the scene the way it is? It's because the world is made of objects. Objects have surfaces. Every picture you see is projected from the 3D world. Right, so 3D to 2D projection, surfaces, objects, occlusions are universal. So these are really the minimal but also universal causal structure behind visual data. We're not trying to model arbitrary domain knowledge. We're trying to model things that are minimal but also universal, and to integrate integrate them with learning, with machine learning, to let learning to learn what we cannot really model. And it turns out that such kind of minimal but really universal model is the key for our system to generalize better and to perform better. Thank you so much. I think this is the end.
Thank you so much. Thank you so much, Jiajun. It was really great to see your perspective on 3D construction and understanding. I think that most of the work that we talked about has been about 2D images, but of course, for any creation, as you mentioned, we have this prior knowledge about 3D. Have you considered doing anything in the realm of 3D printing? And I think that in future soon,
yeah,
we'll see a lot of those applications of 3D printing.
Not directly in 3D printing, but we are very interested in like 3D shape modeling, CAD models and stuff. Armando and Wojciech, and they collaborated with Autodesk, and they they have a paper called inverse CSG, for optimization of inferring the CSG structure from CAD models. And then they recently have a data set called Fusion 360 Gallery, where they have a lot of CAD models with their corresponding manufacturing the CAD model process. So we're also talking to Autodesk. We have some collaboration with them and see if there's any chance that we can do this kind of inferring the procedures behind those CAD models. So yeah, there's some collaboration there. So we're in general very interested in that part, but we haven't looked into printing, 3D printing.
Yeah, I think that's quite interesting.
Although, of course, I think Wojciech is, like does both. He does a lot of work on 3D modeling, procedural
Right.
modeling, but also into printing and also even designing the materials of
Right.
these objects. Yeah.
Sure. Excellent. Very cool. Is there any question? Well, it was great to have you and appreciate your time and sharing with us what you.
Great. Yeah, nice to see you, Ali. Thanks. Yeah.
All right. Have a
See
good
you.
day.
Bye.